This is the EdExcel A-Level Maths Paper 1 covering the Pure Maths module, and this is from the 2018 series. Question number 1. Given that theta is small and is measured in radians, we have to use the small angle approximations to find an approximate value of 1 subtract cos 4 theta over 2 theta sine 3 theta. Now, when we come to use the small angle approximations, if we go to the formula book, we'll find here for theta in radians, sine theta is approximately equal to theta, and cos theta is approximately equal to 1 minus theta squared over 2. And so, therefore, if we find an approximation for cos 4 theta, this is approximately equal to 1 minus, and then in brackets, 4 theta squared over 2. And if we work out what this is, we have 1 subtract 16 theta squared over 2, which is the same as 1 subtract 8 theta squared. We can also find an approximation for sine 3 theta. That's approximately equal to 3 theta. And so therefore, when we come to find an approximation for 1 minus cos 4 theta divided by 2 theta sine 3 theta, this is approximately equal to, well, we've got 1 minus, and then in brackets, 1 minus 8 theta squared, and then we divide this by 2 theta multiplied by sine 3 theta, which we said is approximately equal to 3 theta. And so, working this out, on the top, 1 subtract 1 is 0, and negative 8 theta squared, that's positive 8 theta squared, and then we divide this by 2 theta times 3 theta, which is 6 theta squared. And if we simplify this, it turns out we get 3/4. Question number 2. A curve C has equation y equals x squared subtract 2x subtract 24 times the square root of x, where x is greater than 0, and for the first part of part A, we have to find dy over dx, and then for the next part, find the second derivative, d squared y over dx squared. Now, before we do anything else, we can rewrite the curve C as y equals x squared subtract 2x subtract 24x to the power of 1/2. And so, for the first part of part A, when we come to find dy over dx, differentiating x squared, we end up with 2x, differentiating negative 2x, we end up with negative 2, and differentiating negative 24x to the half, we end up with negative 12, x to the negative 1/2. And then for the Next part, finding the second derivative d squared y over dx squared. Differentiating 2x, we end up with 2. Differentiating negative 2, we end up with 0. And differentiating negative 12x to the negative 1/2, we end up with positive 6x to the power of negative 3 over 2. Then we have to verify that C has a stationary point when x equals 4. Well, if we want to show that C has a stationary point when x equals 4, we need to show that the first derivative is equal to 0 when x is equal to 4. And so therefore, for part B, when x is equal to 4, dy over dx, that's equal to 2 multiplied by 4, subtract 2, subtract 12, multiplied by 4 to the power of negative 1/2. And it turns out here we get 0. And because the first derivative is equal to 0, we can therefore conclude we've got a stationary point when x is equal to 4. And then for part C, we have to determine the nature of the stationary point, giving a reason for your answer. Well, for us to determine the nature of the stationary point, we substitute into the second derivative. And so therefore, for part C, when x is equal to 4, d squared y over dx squared, that's equal to 2 plus 6 multiplied by 4 to the power of negative 3 over 2. And it turns out here we get 11 over 4. And because this is greater than 0, in other words, the second derivative is greater than 0 when x is equal to 4, we can therefore conclude we have a minimum when x is equal to 4. Question number 3. Figure 1 shows a sector AOB of a circle with centre O and radius r centimeters. The angle AOB is theta radians, and the area of the sector AOB is 11 centimeters squared. Given that the perimeter of the sector is 4 times the length of the arc AB, we have to find the exact value of r. First of all, we know area is equal to 1/2 r squared theta, and we know that the area is 11, so we have 1/2 times by r squared times by theta. This is equal to 11. We also know that the arc length is given by r theta. Now, the arc length is given by AB, so we have r times by theta equals AB. Now, if we find an expression for the perimeter P is equal to r plus r, so those are the radii, and then we add on the arc length r theta. And so we also know that the perimeter of the sector is 4 times the length of the arc AB, and the arc length AB is r theta. And so therefore, we have r plus r theta equaling 4 r times by theta. And simplifying this, we can conclude that 2r is equal to 3r theta, and therefore theta is equal to 2/3. The r's cancel on both sides. And now we can find out what r is by substituting into the area. And so we have 1/2 times r squared times by theta, which is 2/3. This is equal to 11. So 1/3 r squared is equal to 11. R squared is equal to 33. And so therefore, we can conclude r is equal to the square root of 33. Question number 4. The curve with equation y equals 2 times the natural log of 8 subtract x meets the line y equals x at a single point x equals alpha, and for part A we have to show that alpha is in between 3 and 4. Well, for part A of the question, we can see that if this curve meets this line, we can set them equal to each other. Both the curve and the line are equal to y, and so setting them equal to each other, we've got 2 times by the natural log of 8 subtract x equals x. Now, if we rearrange so one of the sides is equal to 0, then what we have is 2 times the natural log of 8 subtract x equals 0, and so we can conclude f of x is equal to 2 times the natural log of 8 subtract x subtract another x, and so what we need to do is substitute in x equals 3 and x equals 4 into f of x. And so if we work out what f of 3 is, we've got 2 times the natural log of 8 subtract 3 subtract another 3. So I've got 2 times the natural log of 8 subtract 3 subtract another 3. It turns out here we get 0.218, etc. And f of 4 is equal to 2 times the natural log of 8 subtract 4 subtract 4. And if I work out what this is, it turns out we get negative 1.227, etc. And so what we can say then, as f of x is continuous in the interval 3 to 4 and is continuous, there is a root between 3 and 4. So f of x is continuous in the interval, so we've got a root between 3 and 4. And then we have figure 2 over here, which shows the graph of y equals 2 times the natural log of 8 minus x, and the graph of y equals x. A student uses the iteration formula xn plus 1 equals 2 times the natural log of 8 minus xn, where n is a natural number, in an attempt to find an approximation for alpha. Using the graph and starting with x1 equaling 4, we have to determine whether or not this iteration formula can be used to find an approximation for alpha, justifying your answer. Well, if I start off at x1 equaling 4 and draw a vertical line up, like so, what we now need to do is draw a horizontal line to y equals x, and from y equals x, we draw a vertical line to the curve, and then from the curve, we draw a horizontal line to y equals x, and then we go down to the curve, and then we go across to the line, and then up to the curve, and then we can continue on with this. Well, for part B then, if we take a look here, we can see our cobweb would spiral inwards, and because of that, we can see that the iteration formula can be used to find an approximation for alpha because we've got convergence. Question number 5. Given that y is equal to 3 sine theta over 2 sine theta plus 2 cos theta, where theta is in between minus pi over 4 and 3 pi over 4, we have to show that dy over d theta is equal to a over 1 plus sine 2 theta, where again theta is in between minus pi over 4 and 3 pi over 4, and a is a rational constant to be found. Well, we are differentiating a quotient, and so we would have to use the quotient rule. We begin by letting u equal 3 sine theta, and so therefore u dash is equal to 3 cos theta. V is equal to 2 sine theta plus 2 cos theta, and therefore V dash is equal to 2 cos theta subtract 2 sine theta. And at this point, using the quotient rule, well, with the quotient rule, we know that dy over d theta will equal v u dash subtract u v dash divided by v squared, where v and u and their derivatives are functions of theta. Using this, we can therefore conclude that dy over d theta, that's equal to, well, we've got v, so that's 2 sine theta plus 2 cos theta times by u dash, which is 3 cos theta, and then we subtract u, which is 3 sine theta, times by v dash, which is 2 cos theta subtract 2 sine theta. And then we divide this by v squared, so we divide this by 2 sine theta plus 2 cos theta all squared. And so, working with this, if I expand along the top, I end up with 6 sine theta cos theta plus 6 cos squared theta subtract 6 sine theta cos theta, and then the minus and the minus give a plus, and then we have positive 6 sine squared theta. And on the bottom, 2 sine theta plus 2 cos theta all squared, we end up with 4 sine squared theta plus 8 sine theta cos theta plus 4 cos squared theta. And at this point, we can recognize that the 6 sine cos theta cos theta cancels, leaving us with 6 cos squared theta plus 6 sin squared theta, and if I factorise out the 6, I've got 6 times by cos squared theta plus sin squared theta. And along the bottom, if I factorise out the 4 from the sin squared and the cos squared, I've got 4 times by sin squared theta plus cos squared theta, and then I add on to this 8 sin theta cos theta. Now, recognising that cos squared theta plus sin squared theta is 1, we have 4 multiplied by 1 plus 8 sin theta cos theta on the bottom, and on the top we've got 6 multiplied by 1. And now what we can do is simplify all this. We've got 6 divided by 4 plus 8 sin theta cos theta, which is the same as 3 over 2 divided by 1 plus 8 sin theta cos theta. And so therefore A is equal to 3 over 2. Question number 6. A circle C has centre A with coordinates 7, 5, and the line L with equation y equals 2x plus 1 is a tangent to C at the point P, as we see in figure 3. For part A, we have to show that the equation of the line PA is 2y plus x equals 7. Well, PA would be the radius, so we need to find the equation of the radius. Now, if we take a look at the line L, we can see straight away that the gradient of L is 2. It's of the form y equals mx plus c. The gradient is 2. And so therefore, the gradient of the radius will be negative 1/2 the negative reciprocal of 2 is negative 1/2. And we know that the circle has centre A, and the line here passes through A with coordinates 7, 5, and therefore the equation of the line will be given by y minus 5 equals minus 1/2 multiplied by x minus 7. And so if we multiply by 2, we've got 2y minus 10 equals negative x plus 14. Rather, negative x plus 7. And so therefore 2y plus x is equal to 17. Next, we have to find an equation for C. Well, what we need to do is find out the length of the radius. We know so far that A has coordinates 7, 5. We can find the coordinates of P, and we can do that by setting L equal to the equation of the tangent. And so if we have y equals 2x plus 1, then we've got 2 times by y, which is 2x plus 1, plus the x. This is equal to 17. 4x plus 2 plus another x is 17. 5x is 15. X is 3. And when x is 3, y would equal 2 multiplied by 3 plus 1, which is 7. And so if I go back to my diagram, to find the coordinates of P, we've got 3, 7, which are the coordinates of P. And so the length PA will be given by the length of the radius. And so therefore, the radius R, which is equal to PA, well, we've got the change in x's, 7 subtract 3 squared, plus the change in y's, 5 subtract 7 squared, then all square rooted. And so if I work out what the radius is, it turns out we have the square root of 20. And knowing that the radius is the square root of 20, we know what the centre is. We can therefore conclude our circle has equation x minus 7 squared plus y minus 5 squared equals 20. And then for part C, the line with equation y equals 2x plus k, where k doesn't equal 1, is also a tangent to C. We have to find the value of the constant. Well, to do this, let's draw a new diagram. So for part C, we've got our circle with centre 7, 5. We've got our point P, which is a tangent to the circle at 3, 7. And we've got this other line, y equals 2x plus k. Now, these lines are parallel to each other. Now, let's suppose that the tangent here intersects at this point. Let's call it D, say. How would we go about finding the coordinates of D? Well, from the 3 to the 7, we add 4, and then from the 7 to the 5, we subtract 2. And so we'd have to do the same thing in this direction. Here we go down by 2, and then go across by 4. And so if I find out the coordinates of D, 7 plus 4 is 11. 5 subtract 2, that's 3. The coordinates of D are 11, 3, and if I use y equals 2x plus k, I can find the value of k substituting this point in. We've got 3 equals 2 times by 11 plus k. K is negative 19. The equation of the tangent is y equals 2x, subtract 19. Question number 7, we are given that k belongs to a set of positive integers, and for part A we have to show that the integral of 2 over 3x minus k with respect to x in between k and 3k is independent of k. Well, to begin with, we can rewrite this as the integral of 2/3 times 3 over 3x minus k between k and 3k with respect to x. Now, the reason we want to do this is because you'd find that the 3's here cancel on the top and bottom, leaving us with this result. But also here, you'd notice that the derivative of the bottom, 3x minus k, is on the top. That's 3. And this allows us to integrate much more easily. And so if we integrate, we have between k and 3k, integrating, we have 2/3 times the natural log of the mod of 3x minus k in between k and 3k. And so if I substitute in for my upper limit, we have 2/3 times the natural log of, well, here I've got 3 times by 3k, which is 9k, subtract another k, so that will be 8k. And then for my lower limit, I've got 2/3 and then the natural log of, well, I've got 3 times by k, which is 3k, subtract another k, so that's 2k. And what we therefore end up with, using the subtraction law of logs, is 2/3 times the natural log of 8k divided by 2k. The k's cancel on the top and bottom, and 8 divided by 2 is 4. And so therefore we end up with 2 times the natural log of 4 divided by 3. And because the result over here does not involve k, we have something which is independent of k. Then for part B, we have to show that the integral of 2 over 2x minus k all squared between k and 2k with respect to x is inversely proportional to k. Well, I'm going to rewrite this integral. For part B, I'm going to rewrite the integral as the integral from k to 2k of 2 multiplied by 2x minus k to the power of minus 2. With respect to x. And if I use the reverse chain rule, add 1 to the power, divide by the new power, and then divide by the derivative of the bracket, it turns out here we would get minus, and then in brackets, 2x minus k to the power of minus 1. And we are evaluating this between k and 2k. So if I substitute in for my upper limit, I've got minus, and then I've got 2 times by 2k, take away another k, all to the minus 1, so that's going to be minus 1 over 3k. For my lower limit, I've got minus, and then here I've got 2 times by k, subtract another k, all to the power of minus 1, so that's going to be minus 1 over k. And so therefore, the minus and the minus give a plus, so I've got 1 over k, subtract 1 over 3k, and it turns out here we end up with 2 over 3k. And 2 over 3k is the same as 2/3 multiplied by 1 over k. You can think of the 2/3 to be the constant of proportionality. And so the result is inversely proportional to k. Question number 8. The depth of water d meters in a harbour on a particular day is modelled by the formula d equals 5 plus 2 sine of 30t degrees, where t is in between 0 and 24, and t is the number of hours after midnight. A boat enters the harbour at 6:30 am and it takes 2 hours to load its cargo. The boat requires the depth of water to be at least 3.8 meters before it can leave the harbour. For part A, we have to find the depth of water in the harbour when the boat enters the harbour. Well, it enters the harbour at 6:30 and we begin at midnight, and so therefore for part A, if we begin at midnight and we are going to 6:30, that would imply that t is equal to 6.5. And so what we would have to do is substitute in t equals 6.5 into d, and that will tell us the depth. So when t equals 6.5, d is equal to 5 plus 2 sine of 30 times by 6.5 degrees. And so if I work out what this is, ensure we are in degrees, we have 5 plus 2 times the sine of 30 times 6.5. So it turns out we get 4.48, etc. And so therefore, the depth is 4.48 meters. Then, for part B, we have to find to the nearest minute the earliest time the boat can leave the harbour. Well, what we need to do here is set d equal to 3.8 and find the required time. So, if I do that for part B, we've got 3.8 equals 5 plus 2 sine of 30t degrees. And so far our domain is in between 0 and 24, and if I change the domain, the new domain, that would be 0, which is less than or equal to 30t, which is less than 720, and we've got degrees here. So if I attempt to solve, I've got minus 1.2 equals 2 sine of 30t degrees. Sine of 30t degrees is equal to minus 0.6, and so therefore 30t, if I find out what the solutions are for this, we've got the inverse sine of minus 0.6, so we have minus 36.86, etc. Store this into A. To find the next value, we do 180 minus this, so the next value is 216.86, etc. Store this into B, and then we've got the 360 repeats which we need to add on. So the next value is going to be 323.13, etc. We'll store this into C, and then we've got b plus 360. So that's 576.86, etc. So we'll store this into D. And so we need to find out, if we go back to the question, the earliest time the boat can leave. So clearly we'd have to reject this one. And if I do this value of b divided by 30, we get 722. But the 722 would have to reject as well because it takes 2 hours to load its cargo. So if I find out the values of t, we've got this value of a divided by 30, which is minus 1.22. The next one, we've got b divided by 30, which is 7.22. Then we've got this value of c divided by 30, which is 10.77. And then we've got this value of d divided by 30, which is 19.22. Now, this value over here, we need to reject. And that's because t must be greater or equal to 0. But then this value over here, we would also have to reject. And that's because we have to wait 2 hours for the cargo to load. And that is what's mentioned over here. And so because we want the earliest time, we can therefore conclude that t is equal to 10.77, etc., which is the only value. Now the question did specify for us to leave our answer to the nearest minute, and so here we'd have 10 hours, and if I subtract 10 from this and then times by 60, it turns out to the nearest minute we have 46 minutes, so we've got 10 hours, 46 minutes. Question number 9. Figure 4 shows a sketch of the curve with the equation x squared subtract 2xy plus 3y squared equals 50. And for part A, we have to show that dy over dx is equal to y minus x over 3y minus x. So for part A of the question, we begin with our curve x squared, subtract 2xy plus 3y squared equals 50. And if I differentiating x squared with respect to x, we have 2x, and differentiating 2xy using the product rule, well, I've got 2y, don't forget the minus, multiplied by the derivative of x, which is just 1, and then I've got x multiplied by the derivative of negative 2y, so that's negative 2x multiplied by dy over dx, and then differentiating 3y squared, I end up with 6y dy over dx. And this is all equal to 0. And then if I divide through by 2, we can see then x minus y minus x dy over dx plus 3y dy over dx that's equal to 0. And so if we take the x minus y to the right hand side and then factorize out a dy over dx on the left hand side, we will be left with 3y subtract x multiplied by dy over dx, and that's equal to y minus x, and if I divide through by 3y minus x, we can therefore conclude that dy over dx is equal to y minus x over 3y minus x. Now for part B, the curve is used to model the shape of a cycle track with both x and y measured in kilometers. Points P and O represent points that are furthest west and furthest east of the origin O, as we see in figure 4. And using part A, we have to find the exact coordinates of the point P. Well, the exact coordinates of the point P occur when dx over dy equals 0. So over here, we've got dx over dy equaling 0 because it's a vertical line, and the same thing here as well. We have dx over dy equaling 0. And so if we know what dy over dx is, part B, dx over dy, that will equal the that will equal the reciprocal of this. So that's 1 over dy over dx. So 1 over this is equal to 3y minus x over y minus x. And we know that dx over dy equals 0, that's when p and y occur. And so we've got 3y subtract x divided by y minus x equals 0. 3y minus x equals 0. And so therefore x is equal to 3y. So what we will do is we will call, well, now that we know that that x is equal to 3y, we can substitute this into our original equation. We'll call this equation 1. And if we substitute into our original equation, we can find out what y is and then find out what x is. So we will substitute this equation, we'll call it equation 2, into equation 1. So if I substitute in equation 2 into equation 1, that means I've got, well, here I've got x squared, so that's going to be 3y squared minus 2xy, so that's minus 2 times by 3y times by y, plus 3y squared. All of this is equal to 50. So I've got 9y squared minus 6y squared plus 3y squared equals 50. Y squared is equal to 25 over 3. And therefore, we can conclude that y is equal to 5 root 3 over 3, and don't forget, because we square root, we need plus minus. So, if we go back to the question, we need to find the exact coordinates of P. So P occurs when y is negative. So when y equals negative 5 root 3 over 3, x will equal 3 times this, so I have 3 times by minus 5 root 3 over 3, which is equal to negative 5 root 3. And so therefore, the coordinates of P, I've got minus 5 root 3 for the x coordinates, and for the y coordinates, I've got negative 5 root 3 over 3. And now for part C, we have to explain briefly how to find the exact coordinates of the point that is furthest north of the origin O. You do not need to carry out this calculation. So what we'll do is, if I go back to the question, you can see it's furthest north here, and it's furthest south here. And at this point, dy over dx is equal to 0, and that's because we've got a horizontal line, and similarly here, we've got dy over dx equaling 0. And so what we need to recognize then is it's furthest north when dy over dx is equal to 0. Now, do we know what dy over dx is? Well, that's this result here. So what we need to do then is set dy over dx, which is y minus x over 3y minus x equal to 0. So we've got y minus x equals 0, in which case y is equal to x. And if I call this equation 3, we can then substitute 3 back into equation 1 and then choose the positive solution. And the reason we choose the positive solution is because north is positive for y. And so therefore, we solve equation 3 with 1 simultaneously to obtain a quadratic, and then we choose the positive solution for furthest north. Question number 10. The height above ground h meters of a passenger on a roller coaster can be modelled by the differential equation dh over dt equals h cos of 0.25t over 40, where t is the time in seconds from the start of the ride. Given that the passenger is 5 meters above the ground at the start of the ride, part A, we have to show that h is equal to 5e to the power of 0.1 sine of 0.25t. Well, for part A, we begin with dh upon dt equaling h cos of 0.25t over 40. Now, what we need to do is solve for h. We want h equals something. And so what we'd have to do is solve this first order differential equation. Our first step would be to separate the variables. And if we separate the variables, we have 40 over h dh, and that's equal to cos of 0.25t dt. And when we separate the variables, we need to integrate both sides. And so if we were to integrate 40 over h with respect to h, we end up with 40 times the natural log of h, and that's equal to, well, if I integrate cos of 0.25t, I end up with 4 sine of 0.25t plus some constant of integration, c. Now I know that when t equals 0, h is equal to 5, and the reason for that is we're given that the passenger is 5 meters above the ground at the start of the ride. And so, using this, on the left hand side we have 40 times the natural log of 5. That's equal to, well, the sign of 0 will be 0, and multiplying that by 4, we get 0, and then we add on c. And so therefore c is equal to 40 times the natural log of 5. And knowing what c is, we can therefore conclude that we have 40 times the natural log of h equals 4 sine of 0.25t plus 40 times the natural log of 5. And at this point, we can divide through by 40, and if we divide through by 40, we end up with the natural log of h equaling, well, 4 divided by 40 is a tenth, or 0.1, and then we've got the sine of 0.25t plus the natural log of 5. And at this point, we need to do the antilog of both sides. And so we have h to the power of 0.1 sine of 0.25t plus the natural log of 5. Rather, h equals e to the power of 0.1 sine of 0.25t plus the natural log of 5. So we have h equals e to the power of 0.1 sine of 0.25t times e to the power of the natural log of 5. And so therefore, in conclusion, we have h equals, well, e to the natural log of 5 is just 5, and then we have e to the power of 0.1 times by the sine of 0.25t as our final answer. And then, for part B, we have to state the maximum height of the passenger above the ground. Well, for part B, we need to recognise that we have a maximum when the sine of 0.25t is equal to 1, and we can think about the graph of sine. And so therefore, h max is equal to 5e to the 0.1 times by 1, and if I work out what this is to three significant figures, 5e to the power of 0.1, that's 5.53. So we have 5.53 meters given to three significant figures. And then for part C, the passenger reaches the maximum height for the second time 2 seconds after the start of the ride. What we have to do is find the value of t. So for part C, the maximum of sine of 0.25t equals 1. Well, we know regularly, if I draw the graph of sine, we've got a maximum here at pi over 2. And so with our transformed graph, and knowing that the maximum of sine of something equals 1, we can therefore see that 0.25t is equal to pi upon 2, and the next value will be pi over 2 plus another 2 pi, which is 5 pi over 2. And so we have 0.25t equals 5 pi upon 2, and so therefore t is equal to 10 pi, so the value of t is equal to 10 pi times, well, 10 pi, which is 31.4 seconds. Question 11. For part A, we have to use the binomial expansions to show that the square root of 1 plus 4x over 1 minus x is approximately 1 plus 5 over 2x subtract 5x squared over 8. Now, for part A, the way we will begin this is to rewrite the 1 plus 4x over 1 minus x square rooted as 1 plus 4x to the power of 1/2 multiplied by 1 minus x to the power of negative 1/2. And we deal with these separately. Now, the formula for the binomial series is shown here. And so, if I deal with the 1 plus 4x to the power of 1/2, using the binomial, our first term is 1, our second term, we have 1/2 times by 4x divided by 1 factorial. The next term, we've got 1/2 times 1/2 subtract 1 times 4x squared divided by 2 factorial. And then we've got higher order terms. And so therefore, I've got 1 plus 2x subtract 2x squared plus higher order terms as the result of this expansion. Next, if we deal with the 1 subtract x to the power of negative 1/2, first term is 1, next term is negative 1/2 times negative x divided by 1 factorial, and for the term after this, we've got negative 1/2 times negative 1/2 subtract 1 times negative x squared divided by 2 factorial, and then we've got higher order terms. And so if I work out what this is, I've got 1 plus 1/2 plus 3 over 8 x squared plus higher order terms. And so, therefore, the expansion of 1 plus 4x to the power of 1/2 multiplied by 1 minus x to the power of minus 1/2, that will be given by, well, I've got this expansion over here, and then I multiply this by the expansion shown here. And now I need to expand all of these terms. So in terms of the numbers, I've got 1 times by 1. In terms, well, let's continue expanding. Then I've got 1 times by, rather here I've got 1/2 x. So I've got 1 plus 1/2 x. Then I've got over here 1 times by 1/2 x. So let's add that on. And then I've got 1 times by the 3/8 x squared. And then I've got 2x times by 1. And then I've got 2x times by 1/2 x. and that gives an x squared. And then I could continue by multiplying the 2x times by the 3/8 x squared, but we don't want anything involving cubes, we just want terms up to. Rather, we've also got the minus 2x squared times by the 1. We only want terms up to x squared, and so working this out, I've got 1 plus 5 over 2x subtract 5/8 x squared, and then I've got higher order terms. Then for the next part, a student substitutes x equals 1/2 into both sides of the approximation that we see in part A, and we do this to find an approximation to root 6. We have to give a reason why the student should not use x equals 1/2. Well, the expansion of 1 plus 4x to the half is valid for the mod of 4x being less than 1, and so therefore the mod of x is less than 1/4, and 1/2 does not satisfy this. Then for part C, we have to substitute x equals 1/11 into the square root of 1 plus 4x over 1 minus x equals 1 plus 5 over 2x minus 5 over 8x squared. To obtain an approximation to root 6, we have to give our answer in its simplest form. So, for part C of the question, I have to use x equals 1 over 11. And so if I use x equals 1 over 11, using the expansion, I've got 1 plus 4 times by 1 over 11 divided by 1 minus 1 over 11 square rooted. And that is approximately 1 plus 5 times by 1 over 11 over 2 subtract 5 multiplied by 1 over 11 squared over 8. So, on the left hand side, we end up with root 6 over 2, and on the right hand side, we end up with 1183 over 968. And so, multiplying this by 2, an approximation for root 6 is therefore 1183 divided by 484. Question number 12. The value v pounds of a vintage car 2 years after it was first valued on the 1st of January 2001 is modelled by the equation v equals ap to the power of t, where a and p are constants, and given that the value of the car was £32,000 on the 1st of January 2005 and £50,000 on the 1st of January 2012, for part A we have to find p to 4 decimal places and show that a is equal to 24,800. Well, from 2001 to 2005, that's 4 years. So, for part A, when t equals 4, we have £32,000 and this is equal to a p to the power of 4, and we'll call this equation 1. When t is equal to 11, the value is 50,000. Now t equals 11, that comes from the 1st of January 2001 to the 1st of January 2012, that's 11 years. And so when t equals 11, we have 50,000 equals ap to the power of 11. We'll call this equation 2. And we can find out what a and p are. We can do equation 2 divided by equation 1. And so, doing so, we have ap to the power of 11 divided by ap to the power of 4. That's equal to 50,000 divided by 32,000. With the a's cancelling and then subtracting the powers with the p's, we've got p to the power of 7 equals 50,000 divided by 32,000, which is 25 over 16. And so therefore, p is the 7th root of 25 over 16. So if I have 25 over 16, and then take the 7th root of this, I end up with 1.0658, etc. And so therefore, the value of p is equal to 1.0658, and that's given to 4 decimal places. And so to find the value of a, we've got the equations here we could use to find out the value of a. We've got 32,000 equals a multiplied by 1.06, etc. to the power of 4. If I find out the value of a, I need to do 32,000 divided by this to the power of 4, which is 24796.8022, and so therefore we can see that a is approximately 24,800, and that's exactly what we wanted to show. Then for part B, we have to, with reference to the model, interpret the value of the constant a and the value of the constant p. Well, a would represent the initial value of the car on the 1st of January 2001, and p would represent the proportional increase each year. Now for part C, using the model, we have to find the year during which the value of the car first exceeds £100,000. So, for part C, we can set our equation equal to 100,000. So we've got 100,000 equals 24,796.8, etc. multiplied by 1.06, etc. to the power of t. We need to find out what t is. So if I rearrange, I've got 1.06, etc. to the power of t. That will equal, well, I've got 100,000 divided by this, which is 4.032, etc. And so therefore, t is equal to log base of 1.06, etc. of 4.032, etc. And if I work out what that is, I've got log base of, well, here I had the 7th root of 25 over 16 of this, and it turns out we get 21.87, etc. And so therefore, we can conclude where it first exceeds 10,000, rather 100,000, that will be the year of 2022. Question number 13, we have to show that the integral from 0 to 2 of 2x times the square root of x plus 2 with respect to x is 32 over 15 multiplied by 2 plus the square root of 2. Now before we do anything else, I'm going to rewrite this result as the integral from 0 to 2 of 2x multiplied by x plus 2 to the power of 1/2. And the reason I'm going to do that is because of it makes the integration slightly easier. Now here we've got two functions which are being multiplied by each other, so we can use integration by parts. We've got u, which is 2x, and therefore u dash, that's equal to 2. We've got v dash, which is x plus 2 to the power of 1/2, and if I integrate this to find out what v is, add 1 to the power, divide by the new power, and then divide by the differential of the bracket. Well, if I add 1 to the power, I have x plus 2 to the power of 3 over 2, and if I divide by the new power, and then the differential of the bracket, which is 1, I end up with 2/3 times x plus 2 to the power of 3 over 2. And now at this point, we can quite happily integrate. So, the integral from 0 to 2 of 2x times x plus 2 to the power of 1/2 with respect to x, I have here, if I open up my bracket, I've got u, which is 2x, times by v, which is 2/3 times x plus 2 to the power of 3 over 2, then close brackets. We are integrating from 0 to 2, and then I subtract the integral from 0 to 2 of v, which is, well, I've got v times by u dash, so that's 4/3 of x plus 2 to the power of 3 over 2. And I'm integrating that with respect to x. So what do I end up with over here? Well, what I end up with is 2x times by 2/3, that will be 4/3 x, and then I'm multiplying that by x plus 2 to the power of 3 over 2. And I'm going to evaluate that between 0 and 2. And then if I work out the integral of 4/3 times x plus 2 to the 3 over 2, we can use the reverse chain rule. If I first of all add 1 to the power, I've got x plus 2 to the power of 5 over 2, and then divide by the new power, 4/3 divided by 5 over 2, that's 8 over 15. So I subtract 8/15 times x plus 2 to the 5 over 2 in between 0 and 2. And now I need to work this out. Well, before that, we can write this as one entire sum. I've got 4/3 x times x plus 2 to the power of 3 over 2, subtract 8 over 15 times x plus 2 to the power of 5 over 2 between 0 and 2. So, for my upper limit, I've got 4 over 3 multiplied by 2 multiplied by 2 plus 2 to the power of 3 over 2, subtract 8 over 15 multiplied by 2 plus 2 to the power of 5 over 2. That's my upper limit, and for my lower limit, I would have 0 subtract 8 over 15 times by 2 to the power of 5 over 2. So let's work all of this out. What I end up with is, well, let's work this out here. I've got 4 over 3 times 2 times by 4 to the power of 3 over 2. That's 64 over 3. And then I subtract from that 8 over 15 times by 4 to the power of 5 over 2. So I get 64 over 15. And then the minus and the minus give a plus. So then I add on 8 over 15 times by 2 to the power of 5 over 2. Now if I work that out, 2 to the power of 5 over 2, I get 5 point something, which is not in the form I really want. But what I can do is recognize that 2 to the power of 5 over 2 is the same as 2 to the power of 1/2 to the power of 5. So I've got 64 over 15 plus 8 over 15 times by, now here 2 to the power of half, that's square root 2. So I've got square root 2 to the power of 5, which is the same as 64 over 15 plus 8 over 15 times by 2 square rooted to the power of 4 times by square root 2. That's the same as square root 2 to the 5. And square root 2 to the power of 4 is just 4. So I've got 64 over 15 plus, well, 8 times by 4 is 32. So I've got 32 over 15 times the square root of 2. And if I work out what all that is, I get 32 over 15 multiplied by 2 plus square root 2. This is my final answer. Question number 14. A curve C has parametric equations x equals 3 plus 2 sine t and y equals 4 plus 2 cos 2t, where t is in between 0 and 2 pi. For part A, we have to show that all points on C satisfy y equals 6 subtract x minus 3 all squared. Well, for part A, we begin with x equals 3 plus 2 sine t, and what this will imply is sine t is equal to x subtract 3 over 2 and what we can also do from here is square. So I've got sine squared t equaling x subtract 3 over 2 squared. I've also got y equals 4 plus 2 cos 2t. Now, cos of 2t, that's 2 cos squared minus 1. So what I've got here then is y equals 4 plus 2 multiplied by 2 cos squared t minus 1. And if I expand and simplify, well, I've got 4 minus 2, which is 2. And if I rearrange for cos squared, we can see that cos squared t is equal to y subtract 2 over 4. Now why would I do that? Well, what I know already is sine squared t plus cos squared t is equivalent to 1. It's a known identity. And so therefore, I've got sine squared, which is x minus 3 over 2 squared, plus cos squared, which is y subtract 2 over 4. This is equal to 1. So, I've got x minus 3 squared over 4 plus y subtract 2 over 4 equals 1, multiplied through by 4, and then rearrange for y. We can see then that y is equal to 6 subtract x minus 3 all squared. And that's exactly what I wanted to show. Then for part B, we have to sketch the curve. Well, before I sketch the curve, what I can see is the maximum of y will be 3, 6, and that's using the complete the square form. So for part B, the maximum of y is 3, 6, that's using the complete the square form. Now we have to find the minimum and maximum values of x. Now we will have a negative quadratic, so I am expecting the shape to look something like this. But I also know that this point is 3, 6. What I need to do is find out where the limits are, essentially. And the reason we've got limits is because our domain is restricted. And the way we can go about this is to think about the maximum and minimum of sine. So, for us to find the minimum and maximum of sine, well, I know what x is, that's 3 plus 2 sine t. So, I know already that the maximum of sine t is 1, and therefore x max is equal to 3 plus 2 times by 1, which is 5. And I also know that the minimum of sine t is negative 1, and therefore the minimum of x will be 3 plus 2 times minus 1, which is 1. And so, when x is 5, y is equal to 6 minus 1, 6 minus 5 lots of 5 subtract 3 squared, which is 2. And when x is 1, y is equal to 6 minus 1 minus 3 all squared, which is also 2. So now I can easily sketch this curve. So our graph looks something like this. We've got a maximum at 3, 6, the point here, 5, 2, the point here, which is 1, 2. And then for the next part of part B, we have to explain briefly why C does not include all of the points of y equals 6 minus x minus 3 all squared, where x is a real number. Well, quite simply, we can't include all values of x because of our domain. So, the domain that's given by 1, which is less than or equal to x, which is less than or equal to 5. And so therefore, x cannot include all real values. Now for part C of the question, the line with the equation x plus y equals k, where k is a constant, intersects at C at two distinct points. You have to state the range of values of k, writing your answers in set notation. Well, for part C, we know that x plus y is equal to k. And if we rearrange for k, rather if we rearrange for y, y is equal to k minus x. Now what's it talking about when it cuts at two distinct points? Well, if it cuts at, if we go back to the question, if it cuts at two distinct points, that means then that the curve and the line would intersect somewhere here. Here I've got the line, and here it intersects at two distinct points, here and here. And this is the line, y equals k minus x. And what we need to do is find the range of values of k for which this is true. So I've got y equals k minus x, and it intersects the graph over here at 0k, and it's got a gradient of -1. Now, if it intersects at two distinct points, what we can do is use the discriminant. What we know is y is equal to k minus x, and we also know that y is equal to 6 minus, and then in brackets, x minus 3 all squared. So let's set them equal to each other, and then use the discriminant. So I've got 6 minus, and then in brackets, x minus 3 all squared. That will equal k minus x. So I've got 6 minus, and then in brackets, x squared subtract 6x plus 9 equals k minus x. So I've got 6 minus x squared plus 6x subtract 9 equals k minus x. And getting everything over to one side, we can see then x squared minus 7x plus k plus 3 is equal to 0. And at this point, if we use the discriminant, b squared minus 4ac being greater than 0, then we've got minus 7 squared minus 4 times 1 times k plus 3 is greater than 0. So I've got 49, subtract 4k, subtract 12 is greater than 0, and therefore k is less than 37/4. Now we know that the domain is 1 to 5, and what we can do is find the value of k for which it passes through this point. So let's write that down. As the domain is 1 to 5, the curve y equals k minus x, that would pass through 1, 5. So it passes through 1, 5 as we see here, and that allows us to have the curve crossing at two distinct points. I can't have anything below the line, such as here, say, can't have that because it won't intersect at 2 points. So between this value and this value is where it would intersect at two distinct points. So if I, rather at 5, 2. So if I use that point 5, 2, I've got 2 equals k minus 5, so therefore k is equal to 7. And therefore, the solution to my inequality, I've got 7 which is less than or equal to k, which is less than 37 over 4. And in set notation, I've got k belonging to a set of real numbers where k can be in between 7 and 37 over 4. So this is my solution.